You will see this simulation throughout the lab as we demonstrate different laws and properties of gases, but we're going to begin the lab with you making a few of your own observations. The first observation is going to come from when we pump the gas into the container. Watch the pressure reading and take note of the first time it registers a pressure. Now, what just happened? Keep watching it. What just happened? What happened at that moment? We'll do it again. Now, let's do it with a different size gas, a littler one. Watch the pressure. Now. In all those cases, when did the pressure reading happen? You should have noticed it happened when the particles hit the side of the container. Pressure is force per amount of area, so each collision applies force to a very small part of the container, and these add up. Now, large particles will move differently than small particles. You'll notice, watch the speed. That's the large particle movement. Watch the speed. And that's the small particle movement. But in both cases, the pressure is the same. Why is that? Let's see if the number of collisions help give an answer to this. We're going to put in one pump, and we're going to watch our wall collision counter. So you can see that our pressure is around 6, like we expect it to be. I'm going to push wall collisions, and you can see in a period of time, in that many seconds, there's 25 wall collisions. Let me try it again. 34 wall collisions, and one more time. 32. So keep those numbers in mind. We're going to clear it. We're going to do it with the other gas. Doing the same period of time. I've got almost 80 wall collisions. 80 again, 90. But when you look at the pressure, it's the same pressure. So the question is, if pressure is based on wall collisions, then why is it that these molecules that are moving faster that have more wall collisions, why do they have the same pressure as a molecule that is moving slower, a larger particle, and that has less wall collisions? The key is the force at which they hit. These smaller particles have less mass. Force is equal to mass times acceleration. They have less mass, and so when they hit the side of the container, they don't hit it with as much force as the larger particles do. The larger particles have a lot more mass, and so therefore they hit it with more force, and so the pressure is the same. So pressure is the collisions that the particles have with the sides of the walls of the container, and those collisions can have a different amount of force depending on the size of the gas. Now go ahead and make some observation about the gas molecules themselves. So we're going to look at this one. Pick one particle and watch it as it moves. Does it have a constant speed? What's changing the speed? Pick one molecule and see if you can track it across. Will it make it across without a collision? Or is it very likely for it to make it across without a collision with another gas particle? Do you think it's predictable? Or is it random? Does it look like the gas molecules, if you took all of their energy together, does it look like over time the movement of the gas is losing energy and eventually the particles will stop moving? Watch what happens to particle movement, gas particle movement, when you increase the temperature. So hopefully you see something different. Now look what happens when you cool it. If you cool a gas enough, you're going to get it close to its liquid or solid state, and it's not going to be very gas-like. So at a low temperature, this is beginning to look less and less like a gas. At a low temperature, a gas is not ideal. Let's get it back up. There's another time that a gas is not going to be very ideal. Let's see what happens if we just put tons and tons of particles in here. Do you see how crowded the particles are getting? They're almost as crowded as a solid or a liquid. Gas particles at very high pressure are not going to behave ideally either.